Okay, let's dive right into lesson 16 of our master course. Today's explainer is all about why position tolerancing is, hands down, the absolute most vital control in your engineering and manufacturing toolkit.
We are kicking things off with a painful reality that honestly, many of you have probably faced on the shop floor. Imagine this scenario. You've got a custom metal component. Let's say it's a critical bolt hole pattern. Every single linear dimension passes inspection. The coordinate dimensions, they check out perfectly. The quality team signs off. But when you go to actually put the mating parts together on the final assembly line, they simply will not fit. Production halts, scrap bins fill up, and, you guessed it, fingers start pointing. So why do parts with perfect linear dimensions fail to assemble?
Well, here is our roadmap for figuring that out today. 1. The assembly problem. 2. Defining true position. 3. Tolerance zones and datum. 4. Inspection and verification. And 5. Common GD&T mistakes. We're going to break down exactly how position tolerancing solves these functional assembly failures using the latest ASME Y145-2018 standard.
Let's start with Section 1, the assembly problem, and the major limitations of coordinate tolerancing.
Think about the fundamental contrast between traditional plus or minus coordinate tolerancing and GD&T position tolerancing. With coordinate dimensions, you are relying on rigid, square boundaries. If you're designing something like engine mounting holes, this naturally leads to tolerance stacking. The center points drift out to the extreme corners of those theoretical squares, pushing the physical holes entirely out of alignment. That accumulation of error is exactly why parts fail to assemble, even when the numbers look totally fine on paper. Position tolerancing, on the other hand, replaces those restrictive squares with boundaries that actually make sense for circular fasteners. It gives you functional location control that actually guarantees a fit.
Moving to Section 2, defining true position, the theoretical exact location.
So, the crucial point here is that true position relies on basic dimensions to set a perfect nominal target before we even think about applying any variation. It defines the theoretically exact location of a feature. Unlike coordinate dimensions that kind of shift the target around based on a chain of tolerances, basic dimensions lock down exactly where the feature should be in a perfect world. Think of an aerospace assembly point. Basic dimensions give you the absolute flawless coordinates in CAD, and true position is the tether that keeps the physical variation in check. From that perfect center, we then define exactly how much a feature's actual position is allowed to vary. To communicate this design intent clearly, we construct the feature control frame layer by layer on our drawings. First up, we start with the position symbol, which looks a bit like a gun sight or circle with a cross in it. Next is the diameter symbol. And this is absolutely critical because it changes a restrictive square zone into a functional cylindrical one, perfectly matching the shape of the fastener going through the hole. Then we add the allowable tolerance value, and finally, the datum references, like A, B, and C, that lock the whole thing in place. A massive mistake here is omitting basic dimensions when using this frame. Without them, the true position literally just doesn't exist.
When a drawing calls out a position tolerance, it translates directly into physical reality. A 0.8 wide tolerance zone literally becomes a physical cylinder that sits perfectly perpendicular to datum plane A and is positioned precisely relative to datum B. It creates a clear, unambiguous boundary for the manufacturer. The center axis of the actual manufactured hole must fall completely within this theoretical cylinder to pass inspection. Simple as that.
Okay, on to Section 3, tolerance zones and datums, building the reference frame. Here's a huge benefit for production. Using geometric dimensioning symbols like position can actually allow for more than 50% greater tolerance zones compared to traditional linear dimensioning. Because you are using a cylindrical zone rather than a square coordinate zone, you capture the functional area in those diagonal corners that a square would just automatically reject. Mathematically, this actually gives the machinist over 57% more functional tolerance area to work with. It drastically reduces scrap because you stop failing perfectly good parts just because their center point happened to fall in the functional corner of a cylinder instead of a rigid square. It's a real game changer.
To measure this consistently, we use a datum reference frame hierarchy to lock down the parts step by step. Imagine you're measuring an electronic enclosure. We start with the primary datum, which is usually a large mating surface, like the base of the enclosure to sit it on. Then we move to the secondary datum, perhaps alongside to stop it from rotating. And finally, the tertiary datum, like a short edge, to stop that final translation.
You have to mathematically constrain the part's 6 degrees of freedom. That's 3 translations along the X, Y, and Z axes and 3 rotations around them to establish a valid datum reference frame. This is just a fundamental concept for both CAD design and the metrology lab. If you don't constrain these degrees of freedom properly, well, the datum positions won't be consistently measurable. Your perfectly good parts will suddenly look like complete scrap during measurement, and a lot of time and money will be wasted arguing over inspection reports.
Section 4. Inspection and Verification. Let's bring this math to the metrology lab. Whether you're inspecting an aluminum casing for the automotive industry using digital calipers, or you're running an advanced coordinate measurement machine for a high-precision medical device, your inspection relies entirely on those datum structures we just established. You absolutely must anchor the part correctly in the physical world exactly as it was anchored in the theoretical CAD world if you want to inspect it correctly. So the real magic in inspection is calculating what's called the virtual condition. Let's think about an internal hole. You take the maximum material condition, which is the absolute smallest allowable hole size, and you subtract the geometric position tolerance. This creates the absolute smallest allowable boundary. Calculating this worst-case scenario guarantees your mating pin will always fit, no matter what happens in manufacturing, because you have mathematically proven the worst acceptable hole will clear the worst acceptable pit. This virtual condition calculates the exact dimensions needed for a functional GO gauge system. By sizing the pins of a GO gauge to this virtual condition, we use what's called an absolute gauge tolerancing, or basically a pessimistic policy. If the part fits over the gauge, it's definitively good. If it doesn't, it fails. This functional check is incredibly fast on the shop floor and ensures with absolute certainty that no defective parts ever slip through the cracks to cause assembly line stoppages.
Section 5. Common GD&T mistakes. Time for some battle-tested advice right from the floor.
Listen to this real quote from a manufacturing engineer on an engineering forum. You expect my laser cut and brake pressed part to hold a 0.5 millimeter positional tolerance 3 bends away from the datum positions? Not going to happen without serious money. That perfectly captures the frustration of applying unrealistically tight tolerances far away from datum references on processes like sheet metal brake pressing that simply cannot hit them without spending a fortune. Designers often treat position like a standard size tolerance, just slapping it on without considering how the part physically bends, warps, or actually behaves in manufacturing.
Other common drafting pitfalls include selecting unstable datums, failing to include basic dimensions on the drawing, or picking completely imaginary points in space to measure from. Sometimes designers use a true position callout just for the sake of using GD&T, without even checking if the manufacturing process, like tube bending or casting, can actually achieve it. You really have to apply tolerances where they matter for function, not just because the CAD software lets you. A perfect example of an outdated practice that causes endless headaches is the concentricity symbol. It controlled opposing median points, which basically made it notoriously hard to measure and incredibly expensive to inspect. Because you were trying to find an invisible midpoint floating in space, it just caused massive confusion. Because of this, it was actually officially removed in the ASME Y14.5 2018 standard. Seriously, just stick to position or run out. The golden rule is this: GD&T should yield a cheaper part and a happier manufacturer. Period. Ultimately, applying proper position controls should clarify your design intent, simplify the inspection process, and lead to much more cost-effective manufacturing. It should absolutely not add unnecessary complexity or drive up your scrap rates. To quickly summarize our core objectives today, position tolerancing is your best tool for replacing restrictive coordinate dimensions with functional cylindrical zones that mirror real-world fasteners. True position defines the exact theoretical location via basic dimensions. Datums constrain your 6 degrees of freedom so that accurate, repeatable inspection is actually possible. And calculating the virtual condition guarantees your parts will always assemble, bridging that gap between design and physical reality. But that leaves us with a fascinating final question. If position tolerancing solves assembly failures at the worst case size, the maximum material condition, what happens to our tolerance zones when a part is manufactured slightly smaller or larger than its maximum material condition? Can we somehow get even more tolerance out of it? We will unlock that secret in the next lesson, Advanced Position Tolerancing, MMC, LMC, RFS, and Bonus Tolerance.